Bigger than that?
Yeah.
You really need it bigger?
Yeah.
Okay. I can do that. How's that?
That's
Okay. Lexi Bronson, why don't you pass that back? Thanks. Okay, here we go. Okay, but before we jump into this problem, let's just quickly review how we're going to approach the distance formula, right? So we said yesterday, remember, oops, that if we've got on the XY plane, if we've got 2 points and we want to calculate either the length of the segment connecting the points or the distance between the points, same thing, right? Let's say that we've got 1 point over here at, well, let's just start off calling this, well, we'll put numbers in. That'll be better. So this one's at negative, how about that one's at negative 4, 1, and this one's at 5, 4. Okay, so we've got this ugly formula called the distance formula, right? I'm going to write it up again, but I prefer you didn't use it this way. We've got this formula, distance equals the square root of the quantity x2 minus x1 squared plus y2 minus y1 squared. That's just a lot to remember. And let me just remind you why, I don't want to spend too much time on this, but I really want you to kind of get why I don't like you memorizing stuff like that. Memorizing is really just not, I mentioned this a little bit yesterday, but it's not a high level of learning. Your brain doesn't attach much significance to it. Your brain attaches much more significance to processes or concepts than it does to, and did I mention, like I asked you about the state capitals yesterday, right? How many people know their state capitals? Or most of them, probably. I mean, maybe, I don't know, maybe you don't say. I mean, I used to know that stuff, but I don't have, probably can't remember 20 of them now, just because I never use it. But things like processes, people learn really well. Real quick, I just want to show you kind of how your brain works. The more you understand this, the better student you're going to be. So just humor me for a second. We're going to leave math for just a second. In your brain, there are the classic kind of brain cells are called neurons. Neurons are little kind of round cells, and you have just a ton of them. I mean, you got billions and billions of them. When in your life do you think you have the most brain cells? Do they grow throughout your life, do you think? What do you think?
Like in your middle or late 20s?
Actually, right about now, for you guys, is just about when you have the most you'll ever have. Your brain mass, the number of neurons doubles from birth to age 5, and then again from age 5 to about high school, and then it's all downhill. Every time, after that, you bump your head, some brain cells die. You get sick, some brain cells die. I mean, things happen, and brain cells die. Does that mean you get dumber? No, it doesn't, because neurons are really not what's important in determining a person's intelligence. What's really critical in determining a person's intelligence is how interconnected they are. Let me draw you a quick little picture here. So if we've got these little neurons, and they just kind of look like that. and they're just spread throughout your brain. By themselves, they don't do very much, okay? But when they get interconnected, they do a lot. If you look at a PET scan, which is a real-time scan of a person's brain when they're thinking about something, or remembering something, or doing math, or something like that, what you notice is that entire regions of their brain light up. It's not just individual cells, it's whole regions. And people that are more intelligent have larger parts of their brain that are interconnected. The way they're interconnected, there's these two kinds of cells. They're called dendrites and axons. And they're like little tentacles that reach out from neuron towards neuron. So this one right here might have some of these things that reach out like so, this little neuron. They're just kind of squiggly little tentacles. And then the other cells also send out these receptor tentacles called dendrites. These are like axons, and then this guy might send out a little, so on and so forth. You know, you get the idea. But when they interconnect, that allows them to send signals electrically from neuron to neuron. And they actually jump through this, they don't even touch. There's just this little gap where chemicals flood across the junction. You'll learn about that if you study biology, you know, later on. But what's really interesting is that that is the part that makes you intelligent. Albert Einstein is sort of the prototypical genius of geniuses, right? I mean, and as a physicist, I can tell you he was. He was a remarkably intelligent person. You know, there are very few people that you could ever discuss in the same breath as Albert Einstein. When he died, his brain was studied in detail. They cut it into very thin sections, and they studied, you know, why is he so different? Do you think his brain was exceptionally large?
Wasn't it heavier?
It was. Yeah, it wasn't large. It was very normal size, but it was really dense. And when people began to study his brain, what they saw is that he didn't have an excess of neurons, you know, just normal amount of neurons, but he had so much of this interconnectedness. His brain was extra dense because it was just filled with these interconnections, you know, between the dendrites and the axons. And that's what made him so intelligent. So the next obvious question is this something that you're born with, or is this something you can develop? And the answer is, it's probably a little bit of both, but it's mostly something you can develop. How do you do that? It's because that's arguably the most important thing you could do in life is you know, enhance your ability to think, right? Everything we do depends on thinking. And there's some really easy ways, and some of them are a little bit bizarre. One of them is athletics. When you engage in skill athletics, like basketball, for example, where you got to do a lot of stuff with, to be a good basketball player, there's a really high level of skill involved. Or tennis, right? I mean, it could be anything really, golf, where you have to have really fine motor coordination. Training your brain to do those kinds of things, you know, to be able to go with your offhand to the hoop. It's stuff that's not natural. When you do that, your brain has to develop the neural pathways to be able to instruct your muscles very precisely how to do those things. And so athletics is one very good example of a way that you can literally make yourself smarter. This is going to sound a little stupid, but if you want to get smarter, one thing you can do is periodically, like say once or twice a week for dinner, just eat with, if you're right-handed, eat with your left hand. Seriously, that's doing things with your left hand. And it's hard to do. Try writing with your left hand sometime. Try throwing a pass with your left hand. I mean, it's hard to do because you're just not used to it. If you're dominantly right-handed, all of the really fine motor skills, if you were going to paint something or write something, or you were going to try to, you know, let's say you're going to take a sliver out with, you'd use your right hand, right? Because your right hand has better dexterity. When you force yourself to use your weak hand to do that, that puts a tremendous stress on your brain to try to find a way to tell the muscles in your left hand to do those really fine motor skills. And it's a really effective way of having your brain literally create these new kinds of cells that make you more intelligent. So it sounds like a silly thing to do, but actually it works. If you were, you know, stuff like that is important, but probably the best thing, the very best things you can do are things that are highly analytical, like math, for example. Math that's one reason, you know, and I understand what people oftentimes, they say, gosh, I just can't stand that. You know, why do we have to do all this math when I'm not really going to use this in life? Well, I've generally got two answers to that. One of them is you don't really know what you're going to do yet. You know, because you might find later in life that you really like, you know, computer programming, or you like, you know, graphic design. You like something that depends on math in some way. So you can't really rule that out. But even a better answer is, if you want to be good at everything else in life, math is a great way to do it. And it doesn't have to be just math. I mean, math is a good way to do it, but also just puzzles, Sudoku, anything where you have to think and conceptualize, that really gives your brain kind of a mental workout. And you can almost think of it like a muscle, like you're lifting weights. So it's good to do this stuff. But even within math, there are certain things that are much better than others. Learning facts, very low level. Not much of this goes on. But if you learn concepts, if you can, instead of knowing what the distance formula is, if you can think to yourself, okay, well, distance formula, now it's just a Pythagorean theorem, right? And that's something that's a very low level fact that we use a lot, so we retain it. But if you can attach a concept to that fact, you won't ever forget it. It's like in athletics. How many people ski, for example? A few people ski, or you wakeboard, or you know, whatever you do. I mean, tell me if this isn't true. If you haven't skied for a while, if you haven't done math maybe, or you haven't studied a subject where there's a lot of memorization for even a few months, don't you kind of forget stuff? I mean, I do, right? But I guarantee, even though I haven't skied for 8 or 9 years, I used to ski a lot, and I guarantee I could get up on skis right now and feel pretty good about it. Within a few hours, I'd be feeling pretty good, you know? I mean, that stuff comes back to you. Why does it come back to you so quickly? Because there's so much of this involved in learning that. The neural network is so dense and it involves so many cells that even if a few of them get disrupted, the other ones can compensate, and quickly you rebuild. Does that make sense? You rebuild the pathways very, very quickly. So you really don't want to learn things that are small pieces of little factoids. That's not good. Avoid that. You know, that's why we have Google, right? If you need to know something, just Google it. Low-level facts are always available to us. Just talk to your phone and ask Siri, and she'll tell you. But she won't be able to tell you how to do a process, because doing a process takes some actual learning. You have to actually develop the intelligence to do that. Does that make sense? There's some other things too. I don't want to spend too much time on it today, but I'll come back to this. I really have a passion as a teacher for showing people how to learn better. I mean, a lot of times in school, this is kind of backwards to me. We throw a bunch of information at you, but we never really talk about, you know, what's the best way to learn this stuff? How can you most effectively learn this? We do a better job in athletics of that kind of thing. You know, in athletics, we are very careful about saying, okay, here's the plan to get you to point A to point B. Here's why we're doing it, but we don't do it in school as much. So I'll spend some time on that this year. But long story short, don't remember that, because you're just going to forget it. What do we do instead? Okay, we want, instead of this one, we want to, remember, we want to think about distance as just being a Pythagorean theorem issue, right? Pythagorean theorem is simple. If I have a right triangle, and even if you've never seen it, I can teach it to you in 1 minute. It's not a big deal. If we call the lengths of the legs A and B and the length of the hypotenuse C, everybody tell me, what's the relationship among the sides? A squared, B squared equals, yeah, okay, there it is, right? So C squared equals A squared plus B squared, right? So for us, let's just make a right triangle out of this, right? This is how we're going to think about it. So if this is 1 point, instead of taking a direct path, which is going to end up being, the hypotenuse, we're going to take a horizontal and vertical path. We're going to do it in 2 steps. If an ant is trying to go from here to here, we're going to instead have him walk horizontally, like he's walking along blocks, let's say. He has to walk along these blocks and then turn the corner and go north or something, right? Then he's going to go north. Okay, and so we'll call this D. What is this down here? Well, the horizontal part is really just how far apart the x coordinates are, right? Because this is the x-axis, right? So we'll call that delta x. And remember, all delta means in math is change in. It's just a change in x, right? We just want to know how far apart are the x values, and this is how far apart are the y values, right? And then the Pythagorean theorem just becomes, if we do that, Pythagorean theorem just becomes, that's my hypotenuse. So that's like C, right? So distance squared equals delta x is like A. delta x squared plus delta y squared, right? And if I don't really want to solve for d squared, I want to solve for distance, right? So what do I do to unsquare that? How do you unsquare something? Square root it, right? If I square root both sides, then this is just going to become d, and on the other side we just get the square root of delta x squared plus delta y squared. Okay, now I want to show you something else here. And this is kind of, actually is important to know about using calculators. Even knowing how to use, because we use calculators a lot in math, and not just for doing calculations, but for graphing, and they're powerful tools. So I want you to notice something here. Come on. Cat's going. Okay, what is negative 5 squared? Positive 25, isn't it? We know a negative times a negative is a positive, right? Okay, so watch this. So negative 5 squared, and when I hit enter I should get 25, right? Oh wow, what happened? Exactly. This is a really common mistake with calculators. What did the calculators are smart, right? They're designed to be smart. They know order of operations. So why did the calculator get negative 25? It actually did the right thing, because we didn't really ask it to tell us what negative 5 squared is. What we really said was negative 1 times 5 squared. If you do order of operations, what comes first, exponents or multiplication? Exponents. And so the calculator knows, because really when I put a negative out in front of a number, what I'm really doing is just I'm saying negative 1 times the number. That's how you got to think about a negative number. So what the calculator did correctly was it said, okay, let's take care of the exponent first. So 5 squared is 25, and now let's multiply it by negative 1. Okay, what do we need to do instead? Yeah, we'd have to actually put parentheses around the negative 5 and then square it, and now it's doing the right thing. Right now the calculator is seeing everything in the parentheses, which is negative 5, squared. Okay, but that's easy to forget, isn't it? I forget that sometimes. So what I would say then is when you're calculating delta x and delta y, wouldn't it be more convenient to have delta x and delta y always be positive? So when you're squaring it, you don't run the risk of making that mistake, okay? So how can we do that? Well, this is what we talked about yesterday. All we have to do is when I calculate delta x, for example, always subtract the lesser value of x from the greater value. And then you'll always get a positive answer for delta x. And delta x really is just the length of that side of the triangle. So it can always be positive. It doesn't make, either way would work, because a negative number or a positive number squared should give you the same result, right? But squaring the negative number could breed mistakes. It's easy to make the mistake I just showed you on the calculator. So what are we going to get here? Delta x is what in this case? What's delta x equal to? What are the x values? Negative 4 and 5, right? Which is bigger? 5. So we'll just go delta x is 5 minus the smaller one, which is negative 4. Subtracting a negative is the same as adding, so we just get positive 9, right? Okay, so then if we're calculating distance, let's fill in the blanks. So delta x is going to be 9 squared. What about the y's? What are the y values? 4 and 1. Good. Which is bigger? Obviously 4. So we get 4 minus 1 equals 3. So then delta y just becomes 3 squared, right? And we end up with the square root of 81 plus 9 is the square root of 90. Okay, now that's an answer. There's two ways you're going to be asked to do this. And on what your question? Okay. So one way is to just round the answer to the nearest hundredth or tenth or something. That's simple. Do I have to, if I'm just going to round my decimal answer, do I need to simplify this radical? I don't, do I? Right? I can just go right to my calculator. Oops. so I could just do square root of 90, and it's going to give me back that decimal. Let's just say we wanted to round to the nearest hundredth. So then this would be roughly equal to what, what would I round to? It's 9.486. That'd be 9.49 to two places, right? 5 to one place. But to two places, it'd be 9.49. Good, okay? Easy. What if, though, I'm also going to ask you on some questions to give me an exact answer. That's not exact, is it? That is exact, but it's not simplified. So this is where we'd have to go back and kind of utilize the skills that we practiced earlier in the year. So we got to break up the square root of 90 then. We got to see, are there any perfect squares that divide into 90?
Yeah.
There's a pretty obvious one. 9, right, 9 does, doesn't it? So we could write this as the square root of 9 times the square root of 10. What's the square root of 9?
3.
And then we're done, aren't we? Because 10 I can't do anything with. There are no perfect squares that divide evenly into 10. So one answer, if I'm asking for a decimal, that's what you'd get. If I'm asking for an exact answer, simplified, that's what you'd get. Make sense? Okay. I want you to try this. So we'll do our grand experiment here. Everybody come on up and